Dr. Dai is an executive research director at SenseTime, and he received his bachelor degree from Tsinghua University in 2009 and his doctoral degree from 2014. He's also a visiting scholar at UCLA from 2012 to 2013. His research interests include object detection, segmentation, and deep learning algorithms in computer vision. He has published more than 30 papers in top conferences and journals, and has gained more than 12,000 citations. So let's welcome Jifeng.
Okay, thanks, Kai. I will share my slides. Okay, can you see my screen?
Yeah.
Okay, yeah, then I will start. Okay, hi everyone. Today my talk today is called Automatic Loss Function Design for Generic Vision Tasks. So let's first take a glance on the general training framework of deep learning. During the forward computation, a backbone network extracts the features from the pre-processed data, and the task-specific head is applied to get the prediction. The prediction and the corresponding ground truth labels are used to compute a loss function. After the forward computation, we perform back propagation by computing the gradients with respect to the network parameters and update the parameters. For training a deep network, there are several components that need to be designed. For example, the pre-processing backbone and the head networks, the loss function, and the training recipe. Currently, these components are either designed by Handcrafting or Automail. Here is an illustration of the Handcrafting approach. For different tasks, researchers have to design different networks and training recipes by hand, and redesign their algorithms if the performance doesn't meet the requirement. As we can see, the network design brings high human cost and requires insight and expertise. On the contrary, Automail uses automated search in change of the manual design. Therefore, they trade computational cost for human cost. Meanwhile, current Automail only focuses on searching for the image classification tasks. Moreover, the concerned components of current Automail works, they are mainly restricted to pre-processing, backbone network, and the training recipes. As we can see, there are some drawbacks in the two kinds of design paradigms. The handcrafting approach requires expertise and high human cost, while current Automail is restricted to some specific components of the deep learning training framework, and it is not generic to different tasks. So here comes the question: can we design the networks in a fully automated manner? Here is an illustration. Given different computer vision tasks and the corresponding evaluation metrics, we would like to use a unified framework for automatically design the networks and the training recipes. The framework outputs deployable networks directly, which is optimized for the given task and the given metric. In this process, there are no additional human costs except for defining the task and the metric. To enable the full automated design, the first step is to develop search frameworks for each of these components. With this framework, the next step is to unify them with a search framework for generic tasks. So among these components, the search for loss function is greatly lacking in investing by previous works. So our first step towards this ambition is to develop a general framework for searching loss functions. Now, we first introduce our paper published on iClear 2021. It's called AutoSegLoss, Searching Metric Surrogates for Semantic Segmentation. Let me first explain why we choose the specific task of semantic segmentation. Yeah, because for the task of semantic segmentation, there are numerous evaluation metrics to measure the quality of the segmentation output. As an example, let's see the image of people riding bicycles. So on the right is two different segmentation prediction of the image, and the results differs when you utilize different evaluation metrics. Some metrics would focus more on the boundary, and others would focus more on the main region of each segment. Since different metrics focus on different aspects of the segmentation quality, we need to use proper evaluation metrics in different scenarios. However, during training, some default loss functions are commonly used, such as the cross-entropy loss. During inference, we choose different evaluation metrics according to the requirement of the application scenario. So therefore, there exists a misalignment between loss functions and the evaluation metrics, which may lead to suboptimal training results. However, most evaluation metrics are non-differentiable and cannot be directly utilized as a training loss. To address this problem, we need to design differentiable loss functions for specific metrics. There are two approaches: manually design and automatically search. As for the manually design approaches, there are some works trying to handcraft the variants of the cross-entropy loss, such as the WCE, weighted CE cross-entropy, and the DPCE, and etc. Other works handcraft the differentiable surrogates of the evaluation metrics by carefully analyzing the properties of the metric. However, manually design requires high human cost for trial and error and cannot be extended to generic tasks. Some works tries to automatically search metric-specific loss functions. For example, the work called AMLFS searches for the compilation of some well-performed handcrafted loss functions. However, this kind of work is limited to existing loss functions, and this still suffers from the misalignment problem. Different from these works, our autoseg loss proposes to search surrogate loss functions for different evaluation metrics. Specifically, we design the search space based on the formulation of the target evaluation metric. To design the search space, first, we revisited the mainstream evaluation metrics in semantic segmentation. Although they were in quite different forms when the previous work proposed these metrics, we found because semantic segmentation, the evaluation is basically based on some operations defined on each pixels, to compare the pixels, in the prediction and the pixels, the segmentation output in the ground truth. Yeah. So we found it can be unified and in some form, and the operators, they share some, limited, very similar operators. Yeah. In this table, we list some common metrics for semantic segmentation. So yeah, these metrics, evaluation metrics, of course, they are non-differentiable, and therefore they cannot directly be utilized as a loss functions. However, by analyzing these evaluation metrics, we find that all of them only include two specific types of non-differentiable operators: the OneHot operation and the logical operation. Therefore, if we can extend these operations to the continuous domain to make them differentiable, we can get the surrogate loss function that can be utilized for training. We now take the MLU as an example to introduce how to extend these operators. First, we handle the OneHot operations. So here, the NCHW, indicates the different channels, in the prediction and in the ground truth. Yeah. So this is very simple for ACMarks. We just replace it with a common utilized softmax to make it differentiable. And the other important non-differentiable part that need to be handled is the logical operation. The logical operators are designed on discrete values, 0 and 1. Yeah. Following the truth table of the logical operations, we can write them as fn and f-or. Then, by naively extending the domain of these logical operators from the discrete values to the continuous range, 0 and 1. These functions can be made trivially continuous. However, there is no guarantee that these trivial extensions can drive the network training well. Yeah, because they may lead to some not quite good loss surfaces when driving the network training. In fact, we find that direct using the extended fn and f-or results in very poor performance if we utilize them as the loss functions, okay, which is shown in our paper. So to adjust the gradients of these extended logical functions, we introduce a G function, which remaps the y1 and y2 to the real domain. The G function has parameters theta that can be adjusted. So the loss surface, when you drive network training, can be controlled by these parameters. Here we show the parameterization of the AND function denoted by h_AND. By introducing the G function, we can optimize the parameterized logical functions according to the performance when driving network training. Finally, and we add 2 constraints to make the search space more compact. Yeah, the first one is the truth table constraint, which enforces that the parameterized function takes the same values as the corresponding logical operators. The second one is the monotonicity constraint, which enforces that the parameterized and or are not decreasing on the range, 0 and 1. The process of extending the matrix to surrogate is summarized here. So we realize the parameterized surface on the bottom. After extending, the logical operations they are interpreted to a continuous surface defined on the range between 0 and 1. Yeah. By adjusting the parameters theta, we can optimize the surface shape to make the surrogate loss functions can drive the network training well. After extending the non-differentiable matrix to obtain the parameterized loss functions, we have constructed our search space, which has the parameter theta. Okay. Now we can perform parameter search to optimize these surrogate losses. We employ a reinforcement learning algorithm for searching. First, we sample several thetas from a truncated Gaussian distribution, and which form a batch of different surrogate losses. We then use these surrogate losses to train a batch of networks. After the network training, we evaluate these networks on a holdout validation set with a target evaluation matrix. For example, mean IOU. These evaluation scores are used as a reward signals in the reinforcement learning algorithm to derive the policy gradients. We use the policy gradients to update the mean value of the Gaussian distribution. Through this way, the distribution is pushed towards a better direction. After several cycles of sampling and updating, we obtain the searched optimal parameters theta star. We substitute the non-differentiable components in the surrogate matrix with the searched extensions and obtain the surrogate loss function. These functions can be used to train our semantic segmentation networks. After several cycles, okay. AutoSegLoss is designed to incorporate with segmentation. During the search, AutoSegLoss passes the candidate loss functions to segmentation framework. Then the segmentation component returns the evaluation score. After the search, AutoSegLoss gives the search the loss functions, and they can be used for network training with segmentation. So it can be integrated very easily with the wonderful segmentation framework. Now we will discuss about the experimental results. First, we conduct a search targeting to different evaluation metrics on two popular data sets, Pascal VOC and cityscapes. Our baselines are the commonly used handcrafted loss functions. On each evaluation metric, our searched loss functions is on par or even better compared with the existing handcrafted loss functions. It proves that our search framework is very effective. For example, on the boundary metrics such as the boundary F1 score, the search loss functions show a huge performance improvement. This is because we will optimize, specifically for the given metric, while the existing loss functions suffer from the misalignment issue. We verify the generalization ability of the searched loss functions in two aspects, generalization among data sets and the generalization among frameworks. As shown in the table, we can just search for the function just once, and it can be the search loss function itself, can be fixed and it can be applied to different data sets and applied on different backbone networks. Okay. So let's make a summary. So it's the first general framework for searching surrogate loss functions for mainstream semantic segmentation metrics. We proposed an effective parameter regularization and search algorithm. And the search loss functions, it has a good property that it can be generalized well to other data sets and networks. So the challenge is that, so we still, so this work is still restricted to a specific task of semantic segmentation. We took advantage of the properties of the task semantic segmentation at hand, so we can design, a unified search space, to parameterize the surrogate loss functions. So our next ambition is that can we search loss functions, for more generic tasks and for more evaluation metrics for these very different tasks. Yeah, here comes our next paper. It is called AutoLoss 0, searching loss functions from scratch for generic tasks. So we named the framework 0 because it searches from scratch and with minimal human expertise. Our target is to develop a general framework for searching loss functions for any given tasks and any evaluation metrics. So here comes a very important challenge that, the different tasks and evaluation metrics, they are heterogeneous. So to make our framework generally applicable to different computer vision tasks and different evaluation metrics, we should design the search space and search algorithm carefully. Specifically, we should only utilize the basic primitive operators to construct the search space so that no task-specific human heuristics are involved. The freedom of the search space makes it very large. Therefore, the search algorithm should be efficient enough to explore the huge search space. Yeah, here comes the challenge. So let's see how we do this. So we construct the search space with primitive mathematical operators. Here is a list of our candidate operators. The same operator list is used for all these tasks. As you can see, they are all very basic mathematical functions, and they do not involve any, specific designs for some specific task and metrics. The loss functions are represented by computational graphs with each node selects from the input, output, and the candidate primitive operators. This graph is an illustration of the cross-entropy loss function. The input of the loss functions are the network predictions and ground truth labels. As you can see, the commonly utilized cross-entropy loss function can be represented by this in this computational graph and by these primitive operators in this way. Okay. To explore in this highly flexible search space, we involve the evolutionary algorithm for search. Of course, this algorithm is commonly used for Automail. Yeah, so we'll just skip this part. So this is just a standard evolutionary search framework. Okay. For the loss function, in the mutation, which is the key step in evolutionary search. So we just take these three kinds of standard, operators. That is insertion, deletion, and replacement, and they basically make some mutations on the computational graph of some individuals. However, the naive evolution search is too computationally expensive to explore in this huge search space. For example, in 48 hours, you can only explore about 300 loss functions, because the loss functions we need to train them, for some iterations on the training data set, and to say, okay, whether this loss function can drive the network training well. So if we explore all of them, so this will be very, very slow. So we have to. So in this paper, we introduced some key techniques to speed up the search process, to make the search process much more efficient. Okay, they are loss rejection, gradient equivalence check, and the other one is some simple one that stop training for invalid loss values. And these three techniques can speed up the training, the search, by a lot. The loss rejection protocol is used when producing the offsprings. We develop a fast rejector that efficiently filter out the unpromising loss functions which cannot optimize towards a target evaluation metric. If the generated offspring is unpromising, we reject it and repeat the mutation until the offspring passes the loss rejection protocol. As there are a large amount of unpromising loss functions, this technique can skip many unnecessary network trainings. The second technique is the gradient equivalence check strategy. This one is to avoid the duplicated evaluations of the mathematically equivalent loss functions. Although they are mathematically very similar, but they can be quite different in the computational graph. Yeah, to check the equivalence, we compute the gradients of the candidate loss functions and compare them with the previous loss functions. If the loss function is equivalent, meet our standard, we reuse the previous scores and skip the network training. So yeah, then let's see how can our algorithm can be integrated with OpenMMLab. So AutoLoss0, it can be integrated into OpenMMLab very easily as a general loss function search module. The task-specific framework provides the training and inference API for evaluation candidate loss functions. Okay. So let's come to the experiments. We verify the effectiveness of the AutoLoss0 on a variety of convolution tasks. Let's first see the results on semantic segmentation. On semantic segmentation, we search for the sinks mainstream metrics and achieve competitive results for all these metrics compared with AutoSegLose, which is denoted as ASL here. However, So basically, the results are on par, but remember that for AutoSegLose, it exploits the task-specific heuristics of semantic segmentation. Meanwhile, AutoLoss0, it did not exploit any task-specific heuristics. It is more generic and requires much less human expertise. We also verify our effectiveness on more tasks, such as object detection, instance segmentation, and pose estimation. The extensive experiments show that our searched losses are on par or even better compared with the previous best handcrafted or searched loss functions on these various computer vision tasks. Similar to AutoSegLose, also verifies the generalization ability of the searched loss function over different data sets and networks. So basically, the results show that you can just search for the loss functions just once, on a proper data set and the proper network. And when I say proper, it means that data set is not too easy or the network is not too small, like that. Okay, the loss function then can be fixed and it can be applied for different tasks. Okay, then that is the search efficiency, and by this introduce the strategies specifically designed for loss functions, we can improve the search efficiency by a lot. So the takeaway is that AutoSegLose, SegLoss is AutoLoss0 is the first general framework for searching loss functions from scratch for generic tasks. A novel loss rejection protocol and the gradient equivalence check strategy, they can greatly improve the search efficiency, and they are generally applicable to various computer vision tasks and the metrics. And the search loss functions show competitive performance and can be transferred across different models and data sets. Yeah, that's all. My talk today. Thanks for your time, and I would like to take any questions. Yeah.
Hello, can you hear me?
1 minute. I turn. Yeah. Okay. Hello.
Thanks to Jifeng. I have a question. I noticed we can search the loss function in a different task and evolve the metrics. If I search a better loss function for the specific task, must I need to train the network more difficult?
What do you mean by if you searched for if you found a better loss function? So you would what makes the training more difficult? I did not get your point.
Yes, it means I will to train the network cost 2 resources and cost 2 time.
Oh, I don't think so. First, so the computational cost for searching the loss functions, automatically the cost is that in our experiments, we found that it's not that huge, as you may perhaps you may imagine if it is very huge. However, we found it just took reasonable time. We just utilized like 32 V100, this kind of GPU loads, and for just one round of search, just took like within 48 hours, kind of like that. And the search loss functions, it can be fixed. Okay, then you can utilize the loss function on other data sets and on other backbone networks. You can the just loss function itself is just fixed, and you can just apply them to it can be generalized, it can be transferred to other data sets and other backbone networks. So in my understanding, the efficiency or computational cost is affordable. Yeah. Does that answer your question? I don't know.
Okay, thank you.
Okay, thanks.
Hi, Professor, can I ask a question?
Yeah, sure.
Oh, sorry. Maybe I ask still because this I missed part of the. So I'm interested about your lab provided this is a framework, right? OpenMMLab. It is a framework. What kind of letter structure will apply to? I'm doing the I'm just a new PhD student. I'm doing the YOLO and maybe the others. I want to do the integrated detection and tracking together. So and doing so, you said that it's both the detection accuracy and the tracking accuracy. The loss function can learn to. So they will learn by themselves. My understanding is correct. So I don't design that loss function, or so they will according to the task and the design that and. Sorry.
Yeah, I think I can understand yeah, I kind of understand your question. I will answer it in two ways. First, yeah, of course, this OpenMMLab framework is very well designed, well structured, and our.
Sorry, so Professor, my question is simple. What is input and what is output?
What is the input of this algorithm, right?
Yeah. What is input and what is output? So that will tell. Yeah, I can. Yeah, if I can understand both of the. Yeah, I think. Yeah, I can go deeper.
Yeah. I just try to answer your question quite soon. Okay. Yeah. So basically, because it's just so the major part of our algorithm is a search. It's a search process. Okay. For the search process, so the specific task specific algorithm or code. For example, if you utilize a third party YOLO or other object detectors or trackers, you just need to provide, we just need to train it, to just like in common, object detector, that kind of training, you just apply the loss function to the detector and train it for very short rounds, and you get the result, whether it's loss function can derive good results or bad results, and then it only need to do this after the evaluation result. It fed back to the search.
Understand. Okay, understand. Yeah. Okay, maybe we just search and do a comparison and find the best one.
Yeah. It just only need to do this. Okay.
Oh, okay. Thank you.
Thank you. Yeah. Oh yeah. How different looks? Yeah, I got your question. Yeah. I don't know how to pronounce your name. How different looks the obtained loss functions compared to the traditionals? Yeah, this is a very good question. I can answer that. That is some search the well-performing functions. It looks very similar to the traditional functions. For example, the cross entropy loss. For some metrics and tasks, we can directly find the cross entropy loss function directly by our algorithm, and I find for some very specific tasks, for some other tasks and the evaluation metrics. Let me take one example. For example, for semantic segmentation, some boundary F1 score. This kind of metric, it focuses on the boundaries, and the search the loss function. And it is kind of very interesting. It is quite different to the previous developed ones by human expertise. Yeah, so it depends. Sometimes it is just some core traditional functions, and sometimes there will be some quite different functions. Yeah, that's my answer. Yeah. I think I just take one more question. Okay, and I will, because the time is already late. How soon the auto loss 0 can be released? I expect the performance in IM framework. Oh well, yeah, the paper is under review, and I think after the process, and we can release the code soon. But it depends on the PhD students. They're always quite busy. I will try to push them to release the code soon. Okay. Yeah, thanks. That's all my talk today. I will hand over, the stage to Chen Kai. Okay.
Okay. Thanks to Jifeng. Very good talks. And then we will welcome Wenwei Zhang to share his experience using OpenMMLab to accelerate his research.